Okay, for this video, I'll be going through success criteria G in your pure physics pressure chapter. Okay, so success criteria G, describe the use of a manometer. So this is a new term in the measurement of pressure difference. So for this manometer, it's actually not measuring the actual pressure, it's measuring in terms of pressure difference. Okay, so take note of that. Before that, we are using barometer. Okay, the barometer can actually measure the pressure, the atmospheric pressure. Okay, so pressure difference can be measured using a manometer. A manometer is a U-tube, right? A U-shaped tube containing a liquid. It can either be mercury, oil, and water. Now, because we are measuring a pressure difference, okay, if the pressure difference is not too large, okay, we can actually be using water, even though water's density is low. Okay, so what does the manometer, how does it work? Okay, so we have one end of the tube exposed to atmospheric pressure, or it can also be gas pressure. Remember, it's about the pressure difference. Then on the other side, which is the left hand side, we actually have gas trapped in this part of the U-tube. Okay, so the gas will actually exert a pressure. Okay, and because the right hand side of the tube is lower than the left hand side, the liquid level, we can actually see that the right hand side has a larger pressure. Right hand side's pressure is larger than the pressure exerted by the gas on the left hand side. Okay, so if they are equal level, then they will have the same pressure. Okay, and which means to say if the left hand side's if the depth is lower than the right hand side, then the left hand side will have a larger pressure, so on and so forth. So it is actually measuring the difference in pressure, and we can actually calculate the difference in pressure using our formula. Pressure equals to rho GH. Okay, so the rho will be for the liquid's density, G will be the gravitational field strength of Earth, and H will be the height difference. Okay, so we can look at this diagram and we can say that the difference in pressure is equivalent to a height of 10 cm of water. All right, now of course, if we want to calculate in terms of Pascal, we have to use this formula and then change everything to SI unit to calculate the pressure in Pascal. But if we just look at the diagram, the difference in height is actually 10 cm. So the difference in pressure is equivalent to a height of 10 cm of water. So now if I use the same manometer, and if I go to somewhere else, let's say the atmospheric pressure changed, and now the difference in height is 12 cm, then we can actually say that, right, the difference is now 12 cm, then we can say that, oh, the atmospheric pressure increases. Okay, so without having to actually calculate out the actual pressure difference. Okay, so G1, a sealed U-tube, which is our manometer, contains nitrogen gas of an unknown pressure in one arm. Okay, so it is on the left hand side, and helium gas at pressure P in the other arm. Now the gases are separated by mercury, so this is the liquid that is being used inside, and the density is rho. The dimensions x and y are measured in meters. Okay, so it's already in SI unit. Calculate and express the pressure of the nitrogen gas, okay, using either P, rho, x, or y. Okay, so the way of solving is the same as when we are doing liquid pressure, when we are applying the concepts to barometer. So the first step is always to draw a downward arrow, okay, whenever there's a pressure acting on a liquid surface. Okay, so where do we have to draw the arrows? So over here, okay, because this is the surface of the liquid mercury, so I will say this is Pn, which is my how I denote pressure due to nitrogen gas. Okay, now this is helium, so this will be at pressure P. Okay, so I just need to draw in the arrow. Next step is to find where do we have the same liquid, same level, same pressure. Okay, so we can say that over here we have the same liquid, same level, same pressure, but because the dimensions are not given over here, so it is quite useless. right? So the next best place that I can choose is over here, whereby we have the same liquid, right? Same level, therefore they will have the same pressure. Therefore, I can actually write down pressure due to the nitrogen gas is equals to the pressure due to helium, capital letter P, right? Plus this liquid pressure, right? Because imagine you're over here at this spot, the pressure that's acting upon you is the helium pressure plus the amount of liquid exerting their weight on you, and that is the pressure due to the liquid level. Okay, so we can use rho GH. Okay, so we continue. This is P plus, for this rho, right, is actually the density which is stated over here. So I can leave it as rho. G, I can use 10 because that is the widely accepted G on Earth. Okay, but usually the questions will give, or at the cover page they will state. Now the H is actually the height, which is X. So the final answer will be P, which is the helium's pressure, plus rho 10x, and that is the answer. Okay, question G2, a fork tube contains air in one branch and vacuum in the other. So calculate and express the pressure of the enclosed air using H, D, or K. Okay, so again, there are no numbers given, they are all given in symbols. So let's apply step 1, which is at every liquid surface whereby there's any pressure acting on it, we must draw a downward arrow. So I will draw one here, and I know this is subjected to atmosphere, so this is P atmosphere. Over here, because it's vacuum, so it's nothing, so there's no pressure inside, so I do not need to draw my arrows there. But over here, there will be P air. Okay, pressure due to the air trapped in the right hand side of the branch. Okay, so they want us to calculate this pressure. So where can we have same liquid, same level, same pressure? I can choose over here. Okay, step 2, same liquid, same level, same pressure. So on the right hand side, it is P air, right? Then on the left hand side, it is vacuum, so there's no pressure exerted. So it is this height of mercury that is, or liquid that is exerted on it. Okay, so it is equal to, let me see, okay, due to the liquid is, let's say, density, and the G, and the height is actually not this entire height, it is the height above this level that we chose. Okay, so it will be H minus K. Okay. Okay, so if I am given the density of mercury or the liquid, did they say it's mercury? No. Oh, they say that it's mercury. Okay, so if I'm given the density of mercury, okay, I can substitute in, but in this case, no. Then I have my G to be 10, and this is the height of the liquid that is above the level that we chose. So this will be our answer for pressure due to the enclosed air. Okay, so just follow a 2-step, draw downward arrow, and then apply same liquid, same level, same pressure. Now let's take a look at this. So an open tube stands with one end in a mercury chamber, okay, that's connected to a gas supply over here, right? The atmospheric pressure is H meters of mercury. If it's H meters of mercury, I can write PATM. I can write the density. Actually, I do not need. I just write H meters. The formula is rho GH, right? So I can just do rho G and H, whereby this is the density of mercury, this is our gravitational field strength, and this is the H meters of mercury. Okay, so that's our PATM. Okay, now they want us to calculate and express the pressure of the gas in meters of mercury using H, U, or V. So step 1, draw a downward arrow. So this is P atmosphere, and then over here, this surface, it is P gas. Okay, so step 2, it is finding same liquid, same level, same pressure, and I'll choose this side. Okay, so on inside the open tube is over here, it is due to the pressure due to ATM, atmospheric pressure. Then on the outside, it is equals to P gas. Okay, so P atmosphere is actually rho, G is 10, the height is actually U. Okay, so it will then be equals to pressure due to the gas. Okay, I think I'm missing out something. It's not that simple. Okay, the pressure due to this point is not just P atm. I also need to add in a height of this plus the liquid column, pressure due to liquid. Okay, so that was what I was missing. So P gas is equals to the pressure due to the liquid, which is mercury. So it is rho mercury, G is 10, and the height is U, plus P atm, which is H meters of mercury. So it is using mercury PM, 10, and H. Okay, yes. So what is common is that we have 10 and density of mercury, so it will be U plus H. Okay, so that will be the answer. Now if I give you the value of density of mercury, then you can find the answer. Okay, now G4 diagram shows a manometer used to determine the density of liquid M. When liquid M is poured into one arm, water level in the other arm rises. Okay, so we can actually see that this liquid of which is water, we only need this small height of water to balance off with this height of liquid M, which is actually a higher height of liquid M. Therefore, liquid M must be less dense. Okay, and indeed, in this part, if the density of water and liquid M are 100 and 750, okay, respectively, and you can see that liquid M is actually less dense. Okay, they want us then to calculate the value of H. So again, step 1, draw, okay, any pressure exerted on liquid surface, and it happens that both are PATM. Okay, then we look for same liquid, same level, same pressure. I hope you know by now how to choose it. I will choose here because I have dimensions of 6 cm, I have dimensions of HCM on the right hand side, and over here we have the same liquid, same level, same pressure, which is same liquid of water, same liquid of water. Okay, so let's do the left hand side. Left hand side will be PATM plus 6 cm rho W, okay, which is the density of water, G, and 6 cm of water. So I'll convert it to 0.06. Okay, so this will be equals to the right hand side, right arm's pressure, which is due to PATM, plus rho of liquid M, density of liquid M, G, and the height I can change it to 1 H divided by 100 because it's in HCM, and by right, when I'm using this formula, everything must be in SI unit. Okay, and because both sides are subjected to the same atmospheric pressure, I can actually cancel them out. Okay, so let us now fill in the values. For water, density is 1000 kg per meter cube, G is 10 multiplied by 0.06, which is the height. Then we also have 1000, density of M is actually 750. We have same G and H over 100. Okay, so actually I can cancel away the 10, and if I were to do my calculation correctly, H will get a value of 8.0 cm. Okay, so it's applying the 2 steps. Firstly is drawing any arrows on a surface whereby there's any pressure acting downwards on it, then followed by looking for same liquid, same level, same pressure, and then applying the formulas. Okay.